So in this section 2, we're going to talk about one specific kind of probability distribution. Because here's the deal, guys. Remember last chapter when we were computing these probability distributions by hand? Every once in a while we ran into a situation like we had that in the in-class example with that dice rolling thing where I had to draw the tree diagram and like kind of got involved in terms of building out that probability distribution, right? So what we're going to want to start to do is find like classes of situations where like they behave kind of the same way, even if their probabilities are a little bit different, but they'd be like, I could calculate them in kind of the same way. We'd use kind of the same method. So I can streamline this process of building out a probability distribution in a way that like, you know, makes life a little bit easier, okay? For example, if I was talking about like flipping a coin 50 times, building that tree diagram would stink, right? Like that's a whole like floor's worth of paper by the time you get to the 50th split, right? Where you have like 2 to the 50th power things at the end, and it's like, holy shnikes, this is a mess. But it turns out a situation like that doesn't behave appreciably different than like flipping a coin 3 times. So what we want to do is start making some observations about like these random experiments and seeing like, okay, is this random experiment really kind of set up the same way as this other random experiment? And if so, can I create a procedure for calculating these probabilities independently so I don't have to like build a tree diagram or like really think too hard about this? I can just kind of like plug it into a formula and kind of go. Does that feel okay in terms of like what it is we're trying to accomplish here? And both these two sections to finish chapter 12 will be kind of, that's kind of the point, is we're trying to come up with a method to calculate these probability distributions in a more efficient manner. So the first situation is the binomial distribution. So that's a type of probability distribution. So the definition is just the binomial distribution is the probability distribution obtained from listing the outcomes of a binomial experiment. It's like, great, what the heck's a binomial experiment then? A binomial experiment contains the following properties. So there are a known number of trials performed. That quantity we abbreviate with the letter n. So flipping a coin 50 times, we have 50 trials for our binomial experiment. Are we okay with that? Each trial has only 2 outcomes, either success or failure, like heads or tails. Make or miss, 5 or not 5. Everybody's okay? So an example of a random event that could not be considered a binomial experiment is rolling 2 die and looking at the sum. Because how many outcomes are there for that? 11, right? There's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, you could say, make a binomial experiment out of that if you're rolling 2 die looking at the sum and whether the sum is equal to 7 or not 7. Now it can become a binomial experiment. Is everybody okay with that? Okay, do we feel good about whether something is like success or failure where we have 2 true outcomes to our experiment? Okay. The second attribute is that the probability of success, we'll abbreviate that with the letter P, is constant from trial to trial. That means that these individual trials in our binomial experiment are independent of one another. So if you're talking about drawing cards from a deck without replacing them, no longer can you do a binomial experiment because the probability of pulling the second card is changed if you're not putting it back because now it's out of 51 instead of out of 52, right? But if you're rolling a dice, that's independent. Like if you're hitting a baseball or shooting a basketball or something, that's independent, right? Everybody's okay? And then the last is that all the trials are independent of one another, which goes right along with that probability of success is constant, right? So you can't, that will not be constant if you're not independent. You can have independent events and the probability not being constant from trial to trial. That's still possible depending on the setup. You know, like, if you're talking about like getting dressed or something, and it's like, oh, if I pick a white shirt, you know, there's a 80% chance I'm going to pick blue pants. But if I pick a green shirt, there's a 70% I'm going to pick the khaki pants. You know, like you have a situation like, oh, those are independent events or whatever, kind of. But like, you know, anyway. So if you know the number of trials and the probability of success, you should be able to figure out everything else for your distribution. I should be able to calculate the probabilities of each outcome, 0 through n. And now since there's only 2 outcomes, if we know the probability of success is P, the probability of failure must be 1 minus P. Right? Because there's a 100% chance something happened. Either this thing happened or it did not happen. You add those together, you better get 100%, or else you're operating in some weird world where I don't want to live in, where the laws of probability fail. FYI, we're going to use the lowercase letter q to represent that probability of failure, where q is just 1 minus p. Everybody feel so far so good? Just kind of building out some notation. We haven't really done anything yet, right? We're just deciding like how to name stuff. So one last little piece of notation is I have some random variable x. If the description for the event that random variable is representing is a binomial distribution, I write x and then the squiggle, and then I write a b for binomial, and in parentheses I have n for the number of trials and p for the probability of success. So if we're talking about flipping a coin 50 times, that's our random variable, are the outcomes from flipping a coin 50 times. I would say x squiggle b parenthesis 50 comma 1/2. There's 50 trials because I'm flipping that coin 50 times, and the probability of getting heads is 1/2. Everybody's okay? That is, I'm assuming, again, x is representing the number of heads I get when I flip a coin 50 times. Sorry. All right. So let's give an example here. Let's say determine the probability of getting exactly 2 heads in 3 tosses of a biased coin where the probability of heads is 2/3. So this is a fixed coin where the probability of getting heads is not 50-50. It's weighted one side over the other, so one side's a little heavier, so one side lands down more often. Everybody's okay? So the way we were doing this before was to use a tree diagram, right? So we either get heads or tails. We write in our probabilities of each. That's toss 1. We draw the branches then for toss 2 and 3 and fill them in. And I see, what do we got there? 3 ways to get 2 heads, exactly 2 heads. So to calculate that, I'm going to look at those 3 outcomes where I got exactly 3 heads. I'm going to add those 3 probabilities together because I could get heads, heads, tails, or heads, tails, heads, or tails, heads, heads. And when we say or in probability land, it means add, right? Now to calculate each one of those 3 probabilities, to get heads and then tails, what word did I use there? And, which means multiply. So I just multiply down my path. So I do 2/3 times 2/3 times 1/3 to get the first probability, so 4/27. And I do that for each of those paths. So I end up with 4/27 plus 4/27 plus 4/27, or 12/27, which could reduce down to exactly 4/9. Is everybody okay with that? Now, what we want to do is, instead of building this tree diagram, we want to come up with a formula for this kind of binomial experiment. So if I look at each of those 3 outcomes, heads, heads, tails, heads, tails, heads, and tails, heads, heads, if I simplify down the stuff that I multiplied together, what do you notice? I have 2/3 squared times 1/3 for each of them, right? The probability of getting 2 heads, occurred 3 different ways to get 2 heads, but the probability of each one of those 3 different ways was the same. So if I can calculate, and if I look at that, then I had 2 successes, 2 heads, and 1 failure, the tail, in each of those 3 outcomes, right? They each contain 2 successes because I got 2 heads and 1 tail. If I look at my answer, 2/3 squared times 1/3, that's the probability of success twice and the probability of failure once. Okay, I'm seeing a formula here. The tricky part is, how do I know how many ways that's going to pop up? So that's where we're going to go to next. So again, the end result is all that matters. So it didn't matter how we got 2 heads. The probability was the same for each one of the 3 different ways we could get 2 heads. Correct? We made that observation. And since the order doesn't matter, if I can just calculate the probability of one of those instances and use that for however many times that instance occurs. Okay. To find the total number of instances that I can get 2 heads, I'm going to take the probability of getting 2 heads one time, one way, by the total number of 2-head combinations. When I say the word combination, has anyone other than the students who have sat in an AP statistics classroom heard the term combination in a math classroom? Okay, I didn't know if that was something that gets hit in the AP pre-calculus class or not. Okay, not that you remember, so probably not.
I don't remember my class, but
yeah, if you would have remembered this, it would have happened for a while. So again, the tree diagram was fine, but if I, was flipping this coin 5 times or 6 times or 30 times, ay caramba, no thank you, right? Like, gotta be a better way. So let's look at an example where we've changed this to 6 tosses, and we'll generalize this out a little bit, okay? It's a massive tree diagram, right? No thank you. Let's look at what we got before. So we know that this is a binomial distribution. How do I know it's a binomial distribution? There are a known number of trials performed, namely 6 tosses of the coin. Each trial has only 2 outcomes, success or failure, success being heads and failure being tails. The probability of success is constant from trial to trial. It's always 2/3 because we know that flipping a coin is independent of one another, right? Those are the 4 attributes we need to have. Yes?
Can you go over the whole how you get 2/3 thing again?
It was given to us in the problem,
Okay.
right? It just told us the coin is like not a fair coin, and heads comes up 2/3 of the time rather than half of the time.
Okay.
So it's a coin built to be unfair.
Cute.
Jamie,
Use that.
of course. So before I do anything, I need to check to see if I have a binomial distribution. I need to make sure those 4 attributes are satisfied. Okay, now that we know we have a binomial distribution, we're going to be able to do some stuff here. So symbolically, we can say x is binomial 6, 2/3. Remember, the 6 is the number of trials, and the 2/3 is the probability of success. So that's the name of the specific binomial distribution we're looking at. Okay. Now, all I need is the probability of getting 2 heads once in one way, right? So let's just look at the probability of getting heads, and then 4 tails after. Okay? So I get heads and tails and tails and tails and tails. When I say and, we are multiplying. So I'll just do 2/3 times 2/3 times 1/3 times 1/3 times 1/3 times 1/3, or 2/3 squared times 1/3 to the 4th. So 2 successes, 4 failures. Everybody good? Okay. Now all I need to do is figure out, yes, sure, the number of ways I can get 2 heads if I toss the coin 6 times. That's the tricky part, right? Is figuring out how many different ways I can get exactly 2 heads if I toss a coin 6 times. Right, because I get heads, 4 tails, heads, tails, 3 tails, heads, tails, heads, 2 tails.
Yeah.
And you can see there's going to be a lot of these to count, right? So to do this counting, we're going to take advantage of what's called a combination. So a combination is a situation where the order of individual outcomes does not matter, meaning that you do not care if you get heads, tails, 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 or tails, 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 heads, right? The formula to calculate the number of combinations is given. So on your calculator, the notation will look like that N subscript, C, R subscript. Some textbooks will write it N as a superscript, C with a R as a subscript. The most common notation in a textbook is to write it as a parenthesis n on top, r on bottom, not a fraction. Notice there's no fraction bar there. And the formula to do this is n factorial divided by r factorial times n minus r factorial.
And the factorial thing means like, isn't it all the numbers like less than that?
Right, so like 3 factorial means 3 times 2 times 1.
Okay.
Right. Now, luckily for us, the combination command is built into our graphing calculator, so we don't have to do that by hand. But as Brooklyn mentioned above, the factorial definition is here written below. The one thing to keep in mind is that 1 factorial, 1, and 0 factorial, also 1. Because we need to think about what the factorial is doing. It's talking about the way of counting. How many different ways do I have to arrange 0 things? 1 way, right? That's with, so it's still 0 factorial is still 1. Because we're talking about ways to arrange something. All right. So also worth noting that 6 choose 2 is the same number as 6 choose 4. Because if you think about it, 6 choose 2 is like saying I have 2 successes or 4 failures. 6 choose 4 is saying I have 4 successes and 2 failures. But if I just relabel what's a success and a failure, if I just switch the label from heads to tails, it's still the same thing, right? If we're flipping a coin, I ask you, how many different ways can I get exactly 2 heads? And how many different ways can I get exactly 4 tails? Should be the same number, right? Because it's going to contain the same set of outcomes. So now we can take our probability that we found for one way of getting exactly 2 heads and multiply it by all the different combinations or all the different number of ways I can get those 2 heads by using my combinations formula. So I'm just going to do 6 choose 2. Is everybody okay with that? Now that's a number that I'm going to have to compute using that formula from the other page. So I have n factorial on top divided by r factorial times n minus r factorial. So n is 6, r is 2, and n minus r is 6 minus 2, or 4. So that's where the 6, 2, and 4 are coming from in that formula. So I use my definition of a factorial, and I can reduce some stuff out of there. So really I have 6 times 5 divided by 2 times 1, or just 15. And I multiply across, and I get 60 out of 729, or just a shade over 8% of the time. Is everybody okay with what we've done? Okay. So, now that we've kind of generalized this a little bit, let's go ahead and build this idea out now. So if x is binomially distributed, I can't pronounce anything today, such that x is binomial NP, such that the probability of obtaining r successes out of n independent trials, when p is the probability of success for each trial, is given by the equation, the probability that x is equal to r is going to be n choose r times p to the r times 1 minus p to the n minus r for all r between 0 and n. Well, you should say all integer r's between 0 and n, right? Why does it have to be less than n, or less than or equal to n? We can't get 61 heads if you flip a coin 60 times, right? The probability of that is just 0. That's nonsense. That can't happen. So that's our formula. Everybody feel okay? Now, sometimes we'll rewrite that above formula where we'll use Q instead of 1 minus P. Because remember, Q is the probability of failure, which is just 1 minus P. So depending on where you're reading the formula, they may write it with 1 minus P, they may write it with Q, it's talking about the same thing. Okay? This is not a formula you need to memorize. This is a formula that would be given to you on any quiz or test you'll be taking in this classroom. It's also a formula on the IB exam formula sheet that they give you. So not something you need to worry about memorizing. All right. So let's practice. So we say X is binomial distributed with 6 trials and a probability of success equal to 0.2 for each attempt. Rewrite the situation using symbols. So we'd say X squiggle B parenthesis 6 comma 0.2. Everybody's okay with that?
Yes.
Okay. That's a kind of a question you'd be expected to write on a quiz or a test. Okay. If something's binomial, you'd be expected to write it as a binomial distribution. So let's calculate then the probability of getting exactly 4 successes. So that's going to be using this probability formula, where r is equal to 4. So notice no tree diagram necessary anymore, right? No counting up the number of ways something happens. It just gets plugged into a formula now. This is very nice. What a time saver. So all I'm going to be doing now is plugging into my formula. R is 4, N is 6, P is 0.2. So far, so good. So I can apply my combinations formula. I can expand those factorials and reduce. And then it's just calculator time, right? So I get 48 out of 3,125, or a shade over 1.5%. Does that feel okay?
And then can our calculator do the factorial stuff for us, or do you have to like manually type it?
Brooklyn, it gets better than just that. Just hold on. I'll show you the power of your calculator here in a minute.
Okay.
How about the probability of getting at least 1 success? What does at least one success mean? One or more, right. So we want the probability that x is greater than or equal to 1. Now, what number of successes am I going to have then that are 1 or more? 1 or 2 or 3 or 4 or 5. So I could do that same process 5 times and add them together. Or I could do the complement rule, right? So remember that the probability of x greater than or equal to 1 is equal to 1 minus the probability that x is not greater than or equal to 1. What is x not greater than or equal to 1 the same as? What are the values that are not greater than or equal to 1? Just 0. So I could do, instead of calculating 5 of those probabilities and adding them together, 1 minus the probability x is equal to 0, and just do one of those probability calculations. Which one would you rather do?
The 0.
I would rather do that too. So I'm going to calculate the probability that x is equal to 0. And then do 1 minus that. Boy, that's a heck of a lot easier than doing 4 of them. At least by hand. Doesn't make a lot of difference to your calculator, though. Everybody feel okay? So the probability of getting 3 or fewer successes. Notice here, not a lot of help the complement rule provides, right? Like I can calculate 4 of these probabilities and add them together, or I can do 1 minus 3 of these probabilities. That's not a whole lot of improvement. There, I would say there's preference on what you want to do. So the complement rule won't save you all the time. But when you're very close to one of the ends, buddy, helpful. There we go. Everybody's okay? I think on this one I say we're going to just do it the obvious way. So we're going to calculate P of x equals 0 plus 1 plus 2 plus 3. So again, just plug into my formula, right? The only thing that's changing is the value for r in each one. So it's the bottom number in the combination and then the exponents. But everything else stayed the same. Because n and p are the same. The only place that involve r is the bottom of the combination and the exponents, which are r and n minus r. Everybody feel okay? Okay. All right. Let's again do another example. So we're going to rewrite this using symbols. Probability that I get a bus to work on any morning is 0.4. What is the probability that in a working week of 5 days, will get the bus exactly twice?
0.4 times 0.4 times 0.6.
Before doing any of that, what type of situation is this?
I know.
How do you know?
Because there's 2 outcomes. You either get on the bus or you don't.
Okay. Are they independent?
Yeah.
Is the probabilities constant?
Yeah.
Do I have a finite number of trials?
Yes.
Okay. So first thing I'm going to do is write this as x is binomial. What would the numbers be in the binomial? 5, comma, 0.4. So we're going to define success as catching the bus. And we're looking then for the probability that x is equal to 2. Does everybody feel good? So before you start diving in doing any calculation, you want to be like, is this binomial? Let me check off the things I need to show to make sure it's binomial. If it is binomial, let me write down that it is binomial on my paper now. And since it's binomial, to calculate this probability, all I need to do is use the formula. So just plug in r equals 2 into my formula, and then grind this through on the calculator. Does everybody feel okay about what we're doing? And again, I'll show you guys how to do this binomial distribution on your calculator. You don't even have to use the formula. It's like built into the calculator. We know how to ask it. I'll show you how to ask it. It's very nice. Okay. So, using your graphing calculator. So if you would like to follow along on your graphing calculator, I invite you to take that out to follow along with. If you'd like to borrow a graphing calculator to follow along with, I have 4, and you're welcome to grab one.
Thank you.
Yeah, I'm going to kind of tap dance in place here for a minute in case there's people that are getting their calculator out. We're having to walk up to grab one to borrow. If you wanted to do that, you don't have to. Sometimes sitting and watching is all you need. I'm a hands-on kind of guy. Like, if I don't do it, I don't remember it. You know what I'm saying? All right. First things first, the mode of your calculator doesn't matter. Degree, radian, whatever. Who cares? Doesn't matter for this. Next up, turn that bad boy on. And you're going to press the second button. That's the blue button in the upper left-hand corner. And then the VARS button, which is kind of below the down arrow. Notice above the VARS button is written DISTR, I think. That's short for distributions. So all of your probability distributions live in this menu. So the ones that we are going to be interested in are binomial PDF and binomial CDF. So PDF stands for probability distribution function, and CDF stands for probability cumulative function. If you want the probability that x is equal to one value, that is a PDF. If you want the probability that x is less than or equal to a value, you want CDF. That is something I would write down because it's a common mistake that students make. Okay, probability that x equals r, PDF. Probability that x is less than or equal to r, CDF. Yes, it has to be less than or equal to. That's the way your calculator is built. So if you're like greater than blah, you have to rewrite the problem using like complements to make it a less than or equal to problem. Okay, we'll do some examples of that here in a moment. All right, so when you select for this problem, since it's exactly twice, we're wanting x equals 2, so we pick PDF. When you pick the binomial PDF, you get a menu that pops up that asks for the number of trials, the probability of success, and the number of successes. So we just fill in our values for N, P, and R into our calculator, and then press compute, or calculate, or whatever that, I forget what it, paste, is that what it says?
Paste.
Okay, so that puts it back onto the home screen for you, and if you press enter, it spits out the answer. Ooh. Does anybody have a older calculator where you don't get the menu to pop up? Splendid. I think we're approaching the nexus where like no one's going to have a calculator that is that old enough that doesn't have the newest operating system that has all the menus built in that expects you to like know what all the inputs are in a string and like put commas between them.
Yeah.
So that's great. How easy was that? Way easier than having to do like combinations and factorials and all that nonsense on my calculator, which your calculator can do, but like, do this. Just do this, guys. All right. What if it's the problem if I've changed it? What if it's, I ask, will I blah, 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 get the bus at most twice?
That's the CDF for
What does at most means?
plus than.
Less than or equal to 2. Everybody agree?
Yeah.
So at most twice would mean less than or equal to 2. I could do this with PDFs, right? I could just add up these 3 PDFs. That's fine. That's really just doing the same thing. Or, more efficiently, I can use the CDF function. So if I do 5 trials, 0.4, and 2 successes, for the CDF, I get, spits it right out for me. Okay? Number one thing to keep straight, when do I use the PDF? When do I use the CDF? The CDF must be less than or equal to problems. Okay? If it's not a less than or equal to problem, you have to do some manipulation to rewrite your CDF as a, or your inequality as a less than or equal to. Does everybody feel good so far on the calculator pieces? Okay. New example. When administering a drug, it was known that 80% of people using it were cured. The testing program administered the drug to 2 groups of 10 patients. What is the probability that all 10 patients were cured from both groups? First things first, we need to define a random variable, right? So x will be our random variable. What is it going to represent? The number of patients cured in, I would say in one group.
Okay.
Everybody okay? X is binomial, right? We have a fixed number of trials. The probability of success is known and does not change. Whether one person is cured should be independent of the other person being cured. Okay? So for one group being cured, I have the probability of just over 10%. Note that I did a PDF here because it's x equals 10. So if one group is being cured, everyone is cured, and in another identical group, everyone is cured. What word did I say there?
I get it.
And, which means multiply. So I have p of x equals 10 times p of x equals 10, or I just take this 0.1007 and square it. So just a shade over 1% probability. It's a rare outcome, guys. Is everybody feeling okay on this? Expectation or expected value or mean or average. If I have a binomial distribution, the expected value is n times p. Could you have used the formula that we had listed before to do this? Yeah. Is it way more work? Yeah. Are you crazy not to just do n times p? Yeah, you would be. So for example, if I toss a fair coin 4 times, the expected number of heads to get out of that would be 4 is my number of trials. Half is the probability of success. 4 times a half is 2. That would be how many heads I would expect to get. Everybody's okay? Okay. And we've discussed that. A biased die is thrown 30 times, and the number of 6s seen is 8. The die is thrown a further 12 times. Find the expected number of 6s for those 12 throws. Nope. What do you start with? Deciding if it's binomial or not, right?
Yeah.
Okay. Is it binomial? Yes. Why?
Because either going to be heads or tails.
Okay. Success or failure. Perfect.
And then
And what's success mean?
that the number of sixes should have been in the 12 times that we throw.
So a 6 shows up as a success.
Okay.
And what's a failure?
That another number.
Great. Not a 6.
Okay.
Perfect. Yes. Continue.
And then where it'll be in 12 rows, so that's like the number.
Perfect. 12 trials is a finite number of trials. Yes. Continue.
Wait, what else is it? Oh yeah, they're independent.
Yep.
Okay.
Dice rolls are independent.
Oh, yeah.
Yes. Excellent. And the last thing is that the probability of success is constant,
Oh, okay.
which it is,
Okay.
because it tells us, right? What is the probability of success here? 8 out of 30.
Okay.
Agreed. That's what that initial sentence is telling you in an obscure way,
Yeah.
is that is what we should use as our probability of success. Okay?
Yeah.
All right. So again, we talked through all of this. So if this is binomial 12, 8 out of 30, to find the predicted number of 6s I get, just 12 times 8 out of 30, so 3.2. No big deal, right?
Yeah.
The hardest part was deciding that it was binomial or not,
Yeah.
right? Just making sure we checked it thoroughly.
Yeah.
But once you know what you're looking at, like, it's just plugging into a formula, and the formula is as simple as it gets. It's the product of 2 numbers, guys. We can do this. To calculate the variance, also very simple. N times P times Q. Remember, what is Q the same as? 1 minus P, the probability of failure. Yes. And then what's the relationship between variance and standard deviation? The standard deviation is the square root of the variance. Right. Same thing as what you said, where the variance is standard deviation squared. 6 of one, half dozen in the other. So the standard deviation formula is just going to be yes, it's just the square root of n times p times q. Perfect. Lovely. All right. New example. In a large company, 40% of the workers travel to work on public transportation. A random sample of 15 workers is selected. Find the expected number of workers in this sample that travel to work on public transport. First question you should ask yourself is it binomial? Is it binomial?
Yes.
Okay. Let's not grind that through again because we've done it enough times that I'm confident that you guys know what to check. Okay. Since it is binomial, how do I find the expected value?
40, or is it 40 minus 1, 5, 1, 7?
Yep, n times p.
Yeah.
So the number of trials, which is 15, times the probability of success, which is 0.4.
Why is it W?
W for workers.
Oh.
I don't know. Just it's a random variable name. It doesn't have to make. It doesn't always have to be x. Feel good?
Yeah.
Okay. Find the standard deviation.
So it would just be square root of 15 times 0.4 times 1 minus 0.4 to 0.6.
Yes. Wonderful. So that's
Yep.
the variance, and then to get the standard deviation, we just square root it. And there you go.
Yeah.
You guys can do this.
That's all.
And I think that is the end.
Just this was easier to I think 12.1.
Yes, you know why? Because it's doing the same thing as 12.1, but it's doing it the easier way. I mean, it was hard work to build out the probability distribution that we're using,
Yeah.
but once we had it,
Yeah, the tree diagram like got confusing after a while. I looked at it, I'm like, what's it?
yeah,
I don't know. Yeah, I don't even know what's
all right. In-class examples, let's buzz through some of these. Okay. I'm going to expect some participation from you guys. So please be ready to volunteer. If there's no volunteers, I'm going to pick somebody. I'd like everybody to try to get a work and a chance to respond to something. Yeah.
Oh, the same says comment. Oh, okay.
All right. So first question says there are 12 students in a class, and there are exactly 5 girls and 7 boys. You want to determine the probability of selecting 3 boys in a row with replacement if you were to select only 3 students at random. Everybody hear the situation? Let X be the event that you select a boy. Show that X satisfies the conditions to be a binomial distribution. Who can help us do that? You just need to use the 4 conditions for a binomial distribution.
So it's binomial because you can only get the girl and boys.
Good. Girl and boys like success and failure.
Yep.
Yes.
Independent, they're both independent events.
Right.
And
Why is it? Hold on. Why are they independent? There's a word in here that tells you that this is independent.
Exactly.
Nope.
With
With replacement.
What is that?
Means that if I call on Bob after I call on Bob, his name goes back into the pool, so I could call on him again a second time, so that the number of boys in the pool of names I'm gonna pull stays at 7 no matter what. If I didn't have replacement, not binomial.
Oh, that makes sense.
Everybody's okay?
Yeah, and then the
Okay.
probability would stay the same. Cause it's just, you can't.
Because because the replacement probability stays the same, yes.
And then, what was the last?
Finite number of trials.
Oh, yeah, you get free, wait.
Perfect, yes, 3 trials.
Yeah.
Okay. So we are binomial. Good. How would I write the binomial distribution for this situation?
X equals E, B, N is 12, and P is 5 over 12. I don't know what that.
Neither of those 2 numbers are correct. So N is the number of trials.
Yeah.
So selecting a boy,
There's 3 trials.
yes.
Oh, okay. And then it's 7 over 12.
Yes.
I got the numbers mixed up.
That's okay.
Yeah.
We all make mistakes.
All right.
Mostly, yeah.
Part C says find the exact value of picking exactly 2 boys in the 3 trials. So when I ask for an exact value, what am I looking for? What's an exact value though? Okay, a whole number or
Discrete.
a fraction, right? What does it mean that you didn't do? You didn't do any rounding. So using binomial PDF on this kind of goes out the window. Okay, this is a way for me to ask you to grind out the formula by hand. So what is the probability that I'm calculating? P of X equals 2. No, just 2.
Oh, yeah.
Oh, 'cause it's, yeah.
That's the number of boys I want.
Yeah.
So my formula for a binomial PDF is N choose R times P to the R times Q to the N minus R.
Yeah. Yeah.
And then we just grind this through on our calculator or whatever, and it's
Just gonna crash out, bro. Going home, go home. That's.
Is everybody okay?
Yeah.
How would I check to see that I made sure I did this right? Yeah, I would type this fraction, get the decimal, and then do the binomial PDF and make sure I get the same decimal.
Right.
Is everybody okay?
Yeah.
Right. How do I do D?
So this.
Yeah.
Well, should I be using a CDF or PDF?
It's saying that X is smaller, but it's saying that it equals, so it's X 1. So PDF,
Neither yet.
right? So,
Okay. So what are the possible outcomes when X is less than 2? How many boys names could I pick?
1 and 0.
1 and 0. So you could do this as so you could do it this way with the sum of 2 PDFs, or you could do 1 CDF.
Yeah. Probably would be easier.
Either is fine. I mean, 2 PDFs not that big of a deal to add, but it is easier. But if you don't notice that less than 2 is the same as less than or equal to 1 in a discrete distribution, it's tricky because you have to really understand what you're looking at, right? You have to really understand that, like, oh, the values that x can have are only whole number values, right? Like, so what are the values that are less than 2 that I could get? You have to think about the situation. It all comes back way. Yeah. It all comes back to that. So this comes out to be like 0.376. Okay? And then how about E? CDF, just straight CDF, right? Right. Do that for you guys.
Yeah.
Does that help? Remind you anyways? Okay. Next example. This is probably easier. Why is this a little easier? Yeah, it just gives it to you as a PDF already, right? Or as, I'm sorry, it's a binomial distribution already. All right. Somebody grind out A for us on your calculator. These scream just calculator questions. Go, Olivia. 273, yes. Used a PDF to do that. Who can give us B? Somebody beat Olivia. She's quick with the buttons. She's like, I'm not so. Olivia, go ahead.
0.0879.
Yes.
Oh, this is a different one. Wait, no, wait.
Now look at C.
B is greater than 6.
So it has to be this.
So there's two different plausible ways you could do this. If we wanted to use PDFs, how would we do B is greater than 6?
It's not less than equal to 6. Or it's not, yeah.
So hold on. What are the values that we can have that are less than or equal to 6?
5.
I mean greater than 6. 7 and 8, right?
Yeah.
So you could do it with PDFs that way,
Yeah.
right? Alternatively, you can do a complement. Now, what is not greater than 6?
Greater than, or less than 6.
That's the same as less than or equal to 6,
So that'd be CDF.
and that's a CDF. Could you do it either way?
Yeah.
Yes. Again, it's a matter of preference, I think, at this point.
Yeah.
Is which one is easier for you to interpret, whether you want to just think, oh, greater than 6 is 7 and 8. That's 2 PDFs, let me just add those up. Or do the manipulation with the inequality, which for some of us is straightforward and obvious, and others will look at it and be like, huh?
Yeah.
You know, so I don't think there's the difference between one CDF and 2 PDFs is so small that, Nicole, you have the answer? I saw you trying to raise your hand there.
I have the answer if you want.
What is it?
0.805.
It's not what I got.
It's not.
Did you do the 1 minus?
Nope, sorry. So 0.197.
I had 195 on mine written down, but
Oh, I think I did it wrong. That's right.
either way. All right. Next example, event H. Mr. Chun checks in homework. The probability that Mr. Chun will check in homework on a given day is 0.85. Assuming that each day is independent, write the following events in correct notation, and then use your graphing calculator to solve the indicated probability. So, what do I mean by this?
With the right. Well, the upgrade is a good thing. Like the binomial. No.
Right? That's what we're saying. 4 days in a row. Well, actually, let's do this. Should be H. Okay, so 4 days in a row. So what's the binomial distribution for this? What's the N and the R? If it's 4 days in a row, it's gotta look like that.
Yeah.
Okay. For 3 consecutive days, Mr. Chun checks in homework exactly once. What's the binomial distribution here?
Each. And then in parentheses, 1.
3.
Oh.
0.85. Yes.
Oh, Jackson. Yeah.
Okay. So again, like the challenging part of these questions is not going to be computing the number. It's going to be like making sure you know what you're computing in your calculator, right? The computation is trivial. The calculator will handle that for you. Reading the question and understanding like the binomial distribution and what the probability is that you're looking for. Is the random variable equal to, greater than or equal to, less than or equal to? Okay. In a 5-day week, Mr. Chun checks in homework exactly 3 times.
5, 0.85, and then the H equals 3.
Yes. In a 5-day week, Mr. Chun checks in homework at least 4 days.
So the first part is the same, and then P times H at least, so greater than 4. Yeah.
Okay? But we can't leave it like that if it's going into our calculator, right?
So we less than or
And so.
One minus-
yeah, 1 minus P.
So you guys have said a lot of things, okay? So what are the values that are greater than or equal to 4?
5, 4, 5.
4, no, 4,
4,
5,
5. Okay.
okay?
Yeah.
So, or what are the days that are, so you could do that, right?
Do PDF. Do those.
You could just do a PDF and do this, no problem. Or you could do,
The CDF and do H is less or equal to 3.
so not greater than, or not greater than or equal to 4 is less than 4, which is, since it's discrete, less than or equal to 3. So again, doesn't matter which way you do it. No, I think those two are like equally difficult. Whether you want to use the CDF or 2 PDFs, doesn't matter. Do what you're comfortable with. But that's the 2 realistic ways to do that. Well, you had some wide eyes there. You okay?
I'm good. It's just,
Yup. In 2 consecutive 5-day weeks, Mr. Chun checks in at least 4 days of homework each week.
Oh, so it'd be 5, oh, 0.85. And then it'd be P, what does it say, at least, huh? At least 4, yeah. And then you square it and answer. Yeah.
Everybody okay?
yeah.
So just take our answer from before and multiply by 2. Oh, these are already written down apparently. It's okay. That's the easiest part though, right?
Yeah.
I have a feeling nobody's gonna have a real hard time with
No, don't worry about it.
with those calculations. But I think we're basically at the end here, right?
Yeah.
Okay.
Yeah.
Just as a reminder, I checked in the problem set from Sunday, so you should check to make sure that if you thought something was there, that it was actually there, and if I marked it as missing, you're like, it's there on mine, update or sync your notebook, send me an email, or if you forgot, that happens.
How do you sync the notebook?
So if you just the easiest way to do it is you move your little mouse guy onto the notebook name here,
Yeah.
and then if you right click, one of the options is sync status. That's the one I like to use, and you just hit sync all, and you get like a progress bar on there to show you that your syncing is done. You're sure it's been completed. So mine's taking a minute to sync because I have all of your notebooks
Yeah.
that it's got to pull from, and I'm guessing some of us have opened their notebook from this morning and stuff got pulled, stuff synced in that you hadn't synced in completely, and it takes a minute, but that's the best one.
Right now.
Yeah, so if you got marked as a 0 for missing on the homework and it's there now, shoot me an email and ask me to go back and check, and I'll get those checked in here today or tomorrow. And you'll get a thumbs up back when I get it in, and to know that it got updated.
Yeah. And then you don't have to write that written anyway, or just hi, put it in.
No, you just tell me what you do.
We spilled water all over.
Less is better here.
Right.
Okay, try to-
If it was like an IA, I think that's like, we're just wailing the subject.
No, it is, no, this is as informal as you could possibly be.
I was like,
Last one.
Y'all do it.